Ladies and gentlemen, it's 0800 hours GMT. It gives me very great pleasure on behalf of the steering committee to welcome you to the Asia-Oceania Geosciences Society and European Geosciences Union joint conference series on new dimensions for natural hazards in Asia. My name is David Higgett, and I am, until recently, the AOGS president and part of the steering committee for this event. Now, if things had gone according to plan, we would be in Indonesia right now for the second AOGS-EGU conference. Coronavirus had other ideas, and so we postponed that physical meeting until 2021. So today, you can partly consider this to be a warm-up act for next year's meeting, but we can also consider this a separate event in its own right. And I'm sure many of you over the last few months have been experimenting with video conferences in one way or another. This will very much be a learning experience for us as well. And we're very pleased to get your feedback on how this event goes over the next 3 mornings. Okay, we have 6 conference themes in Monday, Tuesday, Wednesday. Okay, so Monday mornings if you're in Europe, afternoons if you're in Asia, evenings if you're in Oceania, and if anyone's watching from America, you'll have to decide whether it's very late or very early. Okay, our 6 themes are on the screen here. We've also just got a hashtag up here for those of you that would like to put onto Twitter any comments, any pictures from today's session. The session will also be recorded, so you can go back and look at that later. Let me give you a quick housekeeping rules about how these Zoom guidelines will work. We're going to ask all of our panelists to show their videos during each session. For attendees, your microphone and videos will not be functioning, but you will find you have a chat function, so you can post comments to each other, to other participants and attendees. You might have some comments about some of the ideas that are being discussed. If you want to ask a question, please use the question and answer function. So our conveners will be monitoring the Q&A to look for questions to put to the panelists. We won't have enough time to monitor the chat fully. So if you want to ask a question, go to Q&A. If you want to just make some general comments, you can also use the chat. We will be using some other tools, some polling tools, some Padlet, some Google Docs, and so on during today's and sessions over the week ahead. Today we have 2 sessions. The first session theme is on hazard development under a changing climate. The second session, these are only 45 minutes long. Second session is human-induced natural hazards and technological hazards and disasters. So without further ado, let me stop sharing my screen. Okay. Let me hand over to Adam Switzer, who's in Singapore, to introduce the first session today. Adam.
Well, good morning, good afternoon, good evening, wherever you are in the world. It's my pleasure to introduce the first session today. We're going to be examining climate change issues in the context of natural hazards. And so in this case, we're going to look at the serious question of what sort of knowledge, theory, and tools do we need for optimal dynamic assessment and forecasting of natural hazards, particularly in Asia, with changing climate across Asia and Oceania. So we have a great panel with us today. I have a co-convener with me, Kristen Cook. Kristen, perhaps you could quickly just turn on your screen and mic and let everybody know who you are and where you're from. Before you do that, I'll introduce myself. I'm Adam Switzer. I'm a principal investigator at the Earth Observatory of Singapore and an associate professor at the Asian School of the Environment, both of those at Nanyang Technological University in Singapore. I study coastal hazards, and my interest is really in sea level and changing storminess and coastal hazards. Kristen, over to you. What do you get up to?
Yeah, thanks, Adam. So I'm Kristen Cook. I'm a research scientist at the German Research Center for Geosciences in Potsdam. And my main interest is in landslides and flood hazards.
Okay, so thank you very much, Kristen, and she'll be asking some questions later on of our panelists, and I'm going to introduce our panelists one by one. Now, possibly starting with the longest name possible, Srivastan Vijayaragatham. If you could join us, we'll call you Sri for the afternoon to cut down the time.
Yeah, thanks, Adam. I'm Sri from the Tropical Marine Science Institute of the National University of Singapore. I'm more a regional climate scientist working on regional climate downscaling over Southeast Asia and on urban scales over Singapore. And my interest is on climate modeling and climate impacts over this region.
Great, thank you very much, Sri. Our next panelist is Nerali Abram from ANU. So if she could turn on her image, and there you go.
Hi, thanks, Adam. So I'm Nerali Abram. I'm a paleoclimate scientist from the Australian National University. So I particularly work on corals from the Indian Ocean to reconstruct tropical climate variability. I also work in Antarctica, so hence the backdrop that I've got today.
Great. Okay. Yeah, I didn't think you were doing field work in Antarctica at the moment. Okay, and the next speaker is next panelist is Odin Mark. So if Odin, if you could turn on and get ready to give yourself a little introduction, Odin.
Yes, thanks, Adam. So I'm Odin Mark. I'm a junior researcher at CNRS in France, in Toulouse now. And I'm a geomorphologist, geophysicist. And I've been mainly working on landslides caused by earthquakes, storms, and monsoons in Nepal, Taiwan, and Japan mainly, but also in the rest of the world.
Okay, so we've got a modeler, we've got a paleoclimatologist, and we've got a geomorphologist. How about we add in hydrologist? So if I could call back David Higgett. You've already heard from him earlier on in the opening proceedings, but David, if you could come back on board, we can put you on the panel too. David, you're muted.
Hi. Yeah, David Higgett. I'm based in China. I'm a geomorphologist. I work mainly on soil erosion and sediment delivery issues and sediment-related hazards.
Great. Okay. Let's move on. We really do have 45 minutes only, and so we're going to be a little bit strapped for time, and we're going to try and get through this reasonably quickly. One of the things I'd like to do is just get each of the panelists to just talk about a little bit about what they do in a bit more depth, and then in terms of putting it into the context of how we can address issues of climate change in a hazards context going forward. So. If you've got slides, you can share screen, keep it to 3 or 4 if possible. And Sri, I know you don't have many slides, but if you could just give us a little outline of what you're willing to talk about today, so people can use the chat and remember, just everybody out there, stick to the Q&A for asking questions of the panelists and the chat for chatting amongst yourselves. Okay, thank you, Sri. What are you up to?
Yeah, so my research is more on looking into the impacts of climate change in Southeast Asia. And given that we know that GCMs, the global climate models, don't offer much of high resolution information, and therefore it's necessary that we need to downscale to local scales and high resolutions, and that's precisely my work. And it's focused on Singapore, so we do high resolution modeling over Singapore. It's about convection permitting scales about 2 kilometers and higher than that, in fact, about 400 meters. But in a regional scale, we do simulations about 8 to 10 kilometers over entire Southeast Asia. And that links to the hazards, climate hazards like floods, droughts, especially. And I think that's very important in the context of climate risks that this region is facing. And so we believe that the outputs of regional climate models at high resolution can be very useful tools for those impact researchers who are working on floods, droughts, and similar, including like cyclones, for example, which really pose a hazard and climate risk to this region.
Great, thank you, Sri. Okay, Nerali, would you like to share your screen? Hopefully this will come up as full screen.
Good. Okay, can you see that in full screen?
Certainly can.
Excellent. Right, sorry, I need to, there we go. Right, so one of the aspects that I've been working on in terms of paleoclimate is looking at this climate feature that you may have heard of called the Indian Ocean Dipole. It's similar to the El Nino Southern Oscillation, but the El Nino operates in the Pacific. The Indian Ocean dipole operates in the tropical Indian Ocean, and so it has a large impact on Asian countries and also in Australia and Africa. So what you can see in this image here are the sea surface temperature anomalies on the 3rd of October in last year. And this cool sea surface temperature that you can see off the coast of Java and Sumatra is indicative of a positive Indian Ocean dipole event. This was quite a strong record. It was probably equivalent to the strongest record that's been observed. And when we have these cool sea surface temperatures, or cooler than usual sea surface temperatures in the tropical Eastern Indian Ocean, it suppresses the rainfall that we have available. So parts of Indonesia become very dry, parts of Australia become very dry. Over on in Eastern Africa, we have the opposite effect where we see floods. And following this event, we saw the locust plague that's caused problems in East Africa. So in Australia, last summer, we had the Black Summer fires, which were by far the worst forest fires on record in Southeast Australia. That was a coming together of multiple climate factors, including long-term human-caused climate change, but also this very strong positive Indian Ocean dipole event, which contributed to the very hot and very dry conditions and led to these devastating bushfires. So the work that I do is to go and use corals that we can find in the tropical Eastern Indian Ocean. Here you can see divers collecting a core from what we call a Porites coral. A coral like this will have been growing in the ocean for around about 150 years, and so it records a climate history during that time. In Indonesia, we're also, we can find fossil blocks. So this is like an equivalent Porites coral that you can now see upside down in the intertidal area. And this is a coral that was deposited here during the tsunami associated with the Krakatoa eruption. And so what we can do is to piece together a history of that sea surface temperature variability in the Eastern Indian Ocean. And that's what we've been doing. We now have 500 years of data, which gives us a really good perspective to be able to put into context the changes that we're seeing in Indian Ocean dipole events in the observational record, and also what that looks like as we go forward, looking into climate projections of the future. And so we start to see that we are changing this system, and if the trends that are projected continue, we'll soon be moving this system outside of its natural range of variability. So that was everything from me. Thank you.
Great, thank you very much, Nerali. So that's the perspective from a global climate modeler, looking at GCMs, and then a paleoclimate perspective. Maybe move to geomorphologist. If Odin, you could share your slides and give us a little bit of an idea of what you've been up to.
Yes. So I guess you see my screen here. And so I'm working more on the consequences of these extreme climate or meteorological events that we are talking about. And you see here a satellite image, so an optical image in felt color with the vegetation in red and rocks or sediments in gray. And you see there are a lot of landslide scars, these large gray zones all around these landscapes in Taiwan. And they were all caused during a few days of very extreme rainfall in Taiwan in 2009. And there is no scale in the image, but the lake in the center here of this large landslide, they are longer than 1 kilometer. So it's really a huge amount of mass wasting. And the question for landslides is that they are not only depending on the rainfall that may fall during an event, but they are depending on a lot of other parameters. So if you think of the safety factor of a slope here, it will be, the stability of slopes will be modulated by rock or soil, strength, cohesion, permeability, and also then by the amount of rainfall falling in terms of total rainfall, intensity, or antecedent moisture. And this is a really classic view, but some things that are often not thought about by engineers or people thinking in terms of short-term hazards is that the properties of the landscape may also depend on the past condition experienced by the landscape that I showed here. So you can have the landscape evolving with past rainfall and extreme storms, and that will change the properties. So we try to show and evidence this in a recent work that I've been doing in Japan with colleagues. And we looked at the effect of very large typhoons that you see here, Typhoon Talas in 2011 that hit the south of Japan. And on the Key Peninsula here on the coast, there is a fairly large relief, over 1,500 meters. And there were thousands of large landslides that were triggered. And so I show you here on these plots, the landslides are in blacks. So you see there are really a lot on these coastal areas. And you have the total rainfall here on these plots over 2 days, 48 hours, and it's more than 1 meter of rainfall. And you also have the intense rainfall over 2 hours during the typhoon here, above 150 millimeters. But what you see is that when you look especially to the 2 days rainfall, you see it's fairly consistent and homogeneous over the coastal area. And you have large zones where there were very intense rainfall and almost no landslides. And we think that this is due to the fact that because of the orographic effect in this coastal area, there are actually very large differences in the recurrence of extreme rainfall over this small region. And when we normalize the rainfall, so the total amount of rainfall during the event, by the 10 years rainfall, so the rainfall coming only every 10 years, that we could obtain from a long record of radar and data, you obtain this graph on the lower plots. And you see that the anomaly, so how extreme was the rainfall during the event relative to this past rainfall, is much better correlated to the valley where most of the landslide occurred. So it has really important implication if we want to forecast landsliding, and also when we think that landscape have been used to a relatively steady climate, maybe since the Holocene. And with the increase of extreme storms, we may have a drift and much more landslide occurring in some zones that were maybe relatively protected because the landscape had co-evolved with the climate. So that's what I wanted to contribute for the start.
Okay, great. Thank you very much. Okay, I see a few things coming in on the Q&A already. So what we'll do now is perhaps, Kristen, I know we have a couple of things we want to sort of just probe a little deeper with each of our panelists. So I'm going to hand over to my co-convener, Kristen, who needs to unmute herself, and then she'll be able to ask some questions of our panelists. So David, I'll come back to you in a moment with a bit of a big picture question for you. So don't feel left out at the moment.
All right, thanks Adam, and thanks all the panelists for that nice introduction. Yeah, we just wanted to kind of kickstart with some relatively broad, big picture questions for each of you. Well, my screen with the questions just went dark. Yeah, so maybe we'll switch up the order a bit and start with Neroli. Yeah, and so we were wondering, what can we pull out of paleoclimatic records? And as these records improve in resolution and spatial distribution, how do we effectively use them in the context of future natural hazards and future climate change? This is quite a broad question. You can attack it as you like.
Yeah, thanks, Kristen. Yeah, so I think that the really powerful thing about paleoclimate data is not the paleoclimate data itself, even though it's fascinating, but it's the perspective that it gives us, and particularly that long-term perspective. So for example, if we want to understand droughts, our historical record is really short. And so to really understand what the full range of variability is, we really can't assume that the full range is captured in the 100 years or so that we've been taking direct observations, sometimes longer in some places. So I guess a more tangible example, going back to the Indian Ocean dipole, so extreme events like what we saw in 2019 have been historically very rare. So across 500 years of reconstruction, we only see 10 of them. So these have been really unusual events, but when we look at their changing frequency and we compare that to climate model simulations for the future, we see that we're moving into a situation where these events are becoming much more frequent. But another really interesting perspective that we get from that 500 years is that we can see that the strongest events that we have observed so far are not the strongest that are possible. So for example, we reconstructed one event that was around 30 to 40% stronger in terms of how much cooling there was in the Eastern Indian Ocean. And we could trace that back to historical accounts of the upheaval that caused in Southeast Asia. And so that's really important to acknowledge that what we've experienced is not necessarily the most extreme variability that the Earth system can have, even without the extra kick that it's getting from human-caused climate change. And so that's really important from a managing risk kind of perspective.
Great, thank you.
Yep, thanks, Nerly. So maybe we'll go to Odan next. Yeah, we have a question as well in the Q&A that fits in with what I wanted to ask. Yeah, which is it. So your work underscores the strong link between future climate change and hazards in a changing world. And so what are the key tools for integrating climate projection into hazards? And to bring in the Q&A question to maybe make it a bit more specific is how can we determine how frequency and intensity of these extreme rainfall events is changing, and how important is that understanding?
Yes, well, that's not an easy task, because we think to already just with the available data that we have, it's already fairly difficult to constrain extreme climatology on a regional scale. Because if we want to capture the variability of how extreme can be the rainfall in a region, we already need a fairly long time series of rainfall measurements that have been adequately capturing extreme rainfall. And this was already something difficult in the work that I've been doing recently. And Japan was exceptional in this sense, because they have a very long record of radar data where they really can capture the spatial pattern of extreme rainfall and how it's varying over a region. But I think in terms of tools, something really important that still need to be improved and tested further is also the development of the satellite missions. That satellite mission, perhaps coupled with a high resolution climate model, maybe Shri will comment on that, that can help to constrain relatively globally, so in different places of the world, even in places where there are not long, dense network of measurement. With the satellite data, we can constrain the rainfall over the last 15, 20 years, and even capturing the extremes. And this may help to have an idea of which part of the landscape are more or less affected by extremes, and therefore when there is a forecast or when there are some measurements showing that a very large event should occur, we may be able to nowcast maybe in a few years at least the relative intensity of landsliding over a specific region. So that would be an interesting goal, to couple the satellite data and the nowcast data from models, or assimilated data, let's say.
All right, thanks, Adan. So now a question for Shri.
Yeah.
Can you highlight what the key differences will be in CMIP6 and where the inconsistencies are in Southeast Asia?
Well, so some of the model results are still coming out. So as we still continue to evaluate them, I mean, overall, I can give some assumptions to that, is that the models are telling us similar things what the CMIP5 conveyed to us, except that we know that there's a higher sensitivity to CMIP suite of models compared to CMIP5. And therefore, as far as precipitation is concerned, we have the same uncertainty as much as we did have in CMIP5. So we have to a bit more evaluate that for the region. But I would like to link to what Odin mentioned to this, the extremes and what the models say in terms of CMIP5 and CMIP6 and the rainfall extremes, which we are really looking into in detail because of the risks that of floods or droughts or whatever, is that most of these observations we have are very scarce as far as Southeast Asia is concerned. And therefore, some of the events that really happen are lesser in space and time than what the models can really capture. And that is the problem. In Singapore, for example, we do scales of 400 meters, urban scales or something, but we could still have a lesser spatial scale of events. It can happen in extremely short time. And therefore, we need observations where we can really validate the models and check whether that can be in tandem with this. And we haven't reached that yet. And that's really related to extremes and intensities and durations, what you're mentioning about for floods, or especially for flash floods, or for urban scales, where we don't have this intensity, duration, frequency curves well established. And therefore, we are not sure about how extremes will change with respect to sub-hourly scales. I mean, we have a pretty good idea about daily scales. Models are just getting here and there, but sub-daily and sub-hourly is still a challenge. And that's directly linked to the question that we are discussing, is how much can we quantify this hazards with respect to extremes? And that's still being discussed. It's a challenge.
Yeah, thanks, Sri. Shall we move to David now? I don't know if you want to give a brief introduction of yourself, of your work.
Okay, sure. Thank you. Okay, I'm David Higgett. I currently work in China. I'm running a Sino-British university in the north of China, but currently in exile in the UK. So my career is as a geomorphologist, mostly working on sediment-related hazards. Recently, very interested in flood-related hazards. I don't think this is a little bit cheeky, Adam and Kristin, just to highlight that tomorrow we have a session on megacities. We're getting into a period where it's anticipated that 50% of population will be in urban areas. Clearly, one of the great concerns that we have in Asia is the concentration of population into urban areas, the incidence of hazards, particularly flood-related hazards, both from fluvial sources, flash flooding, also coastal flooding and subsidence. And we will talk a little bit about that tomorrow. I've also, in the introduction to today's session, I mentioned that until recently I was AOGS president. If I could maybe just say something very quickly about AOGS as an organization. Very broad-based geoscience society, and one which is committed to making a contribution to understanding of hazards and their impact in Asia and beyond. So I think it's critically important. I think UN has calculated that when people are displaced by hazards, 90% of people displaced by hazards are in Asia. So it's critically important that we understand the impact of changing climate on hazard incidents and its effects on people. Okay, I'll pause at that point because I think we should go to the questions and answers. But if people do have particular questions about AOGS's mission, very happy to answer those in the next couple of days.
Thank you, David. I think we should move to the Q&A. Just a reminder to everybody, a couple of things. The Q&A, press the Q&A down here if you have questions. We have a series of questions coming through. There's a lot coming through already. So while you think of questions, just a little update here. When you use the chat, you can send it to all panelists or all attendees. You can even send it to your friend if you can find them by using find the attendee. So you can message amongst yourselves if you're a panelist, but if you're an attendee, just use the chat sparingly. Some of you are sending it to all panelists when I think you want to send it to all attendees. So just a little update there. Okay, moving on. I think we'll take one question. I want to take something from the Q&A. Uma Das has asked Dr. Abram, could you please comment on the recently observed anomalous warming in the southern Indian Ocean, poleward of 30 degrees south post 2000? So what's happening? Do you know what's happening in the Indian Ocean now? I think it's a very specific question, but we can be specific at this stage.
Yeah, I'm not sure if I'm going to respond to the exact feature that that's been sort of referred to here, because I guess my focus is mostly on the tropics. But one thing we do see is that the Indian Ocean dipole is described as an opposing sea surface temperature anomaly between the eastern equatorial Indian Ocean and the western equatorial Indian Ocean. But we do actually see that particularly the warm anomalies, which are in the Western Indian Ocean, do have an extension down in a southeasterly direction, sort of from the Western Indian Ocean down towards sort of southern, southwestern Australia. So I'm not sure if that's the feature that's being referred to there, but if it is, that is sort of part of that, that dynamic process, even though we define the Indian Ocean dipole as just the anomalies across the equator, there is also the off-equator component. And there has been research that suggested that it's potentially that off-equator component that is a bigger determinant of the rainfall impact in Australia, at least. I'm not sure about other areas.
I'm sure it's all connected. I think one of the issues that we have here in Southeast Asia and Oceania in particular is that we are at the confluence of so many different climate systems that trying to piece this whole story together is probably going to take several lifetimes to get real progress. But the question, one of the fundamental questions we're trying to look at here is, what are the tools that we need? So I think one of the things I'm going to take from the Q&A here is, there was a few questions for Odan, looking at sort of anomalies, things like sediment budgets, and I'm trying to push a couple of questions. There's a lot of questions for you here. So where do you pull rainfall data from, and how can you pull sort of historical records together with the physical evidence and take into account, I think I'm trying to summarize your whole field, take into account things like sediment budgets, and then after an event, the sediment budget's obviously changed. And so how relevant is historical data sets or geological data sets to the future, considering climate is changing?
Yes, yeah, that's a lot of things altogether. I saw also a lot of questions on landslide on the Q&A. For the rainfall data, as I said, it's difficult to get high quality and dense rainfall data. In Japan, this was on the work I showed just before, it was from 26 years old or 26 years continuous records, so of radar data over the whole Japan with high resolution in time, so 1 hour, and in space, a few kilometers. So this was really exceptional data. In other areas where there are not so many radar, like Taiwan, for example, or other places, we can use also rain gauge network and use maybe geostatistical method like kriging or others to try to complement. And in places where there are no local data, I would say it can be tried to check or to look at a combination of models that use reanalysis data and satellite data. So this is for the rainfall data. Then, of course, for the landslide, you also need to have a look, I didn't show it here, but at the topography. So using DM, high resolution, if possible, global, if nothing else is available, to look at slopes distribution, etc. And possibly also lithology or soil cover when it's available. These are things we considered. But even when you have all of these, as I showed in this very simple concept sketch, there are many parameters that we cannot constrain, like permeability of the soil. We know it's hugely varying over different scales, and this is very hard to constrain. So we often have to then rely to empirical scalings or thresholds, and we don't really have a fully deterministic way to predict the hazard of the landslides. And in terms of sediments, yes, I saw a question about sediment budget. Here, what I showed and what I look at is really only the new failures on the slopes. So where we go from a stable slopes with vegetation and no signs of movement that really collapse into the river network or so. But then, of course, after that, it will change a lot the landscape, and we may have a lot of sediment in the river, a landslide dam sometime, and there is a cascade of hazard that can occur with more debris flows occurring in the following years or over types of risk. And this I didn't look at in particular, and it's really a complicated question. We know that sometimes after large storms, some zones become more resilient because the soil have been expurged and there is no more material to fall on or to slide. But in other places, and typically after earthquakes, we have seen that even after a huge amount of landslides, we can still have more landslides occurring because the slopes have changed or because the slopes are damaged. So the question of how one landslide event influence the next landslide event in the same zone is really not solved, and it's a difficult challenge in places like Japan or Taiwan that have landslide, or the Himalayas that have landslide every year. To know if a zone is safer or less safe after a landslide event is really a tricky question.
Great, very comprehensive answer, and I'm sure that there's other questions, but we are really already very quickly running out of time. Just a quick question for Sri. I see there's a question from Vietnam. Just as a note, we have more than 300 participants at the moment, and the questions are piling in. Sri, what do we need to improve our climate models in this part of the world?
Yeah, first of all, I want to mention that it's always it's a thinking that very fine resolution means it's excellent results, but it's not always the case, number one. Therefore, fine scale resolution doesn't mean good results. But of course, there's always a necessity and an earnestness in looking for high resolution climate. For example, if the question is from Vietnam, so I can speak for that. The best way is, you can divide Vietnam into different regions. You have a central highland, and then you have the Mekong region, and then you have a hilly Sapa in the north, and you have a different landscape. The best thing is to have the resolution which you can use an equivalent observation to compare against. So there's no point in running a 5-kilometer RCM simulation of Vietnam when you have at least your data at about 50-kilometer resolution. That's clear mismatch. And therefore, you cannot really validate your model as well. But you might know that there's a new data set which is being developed called VNGP, which uses about 300 stations all over Vietnam on daily scale. So I think it's a pretty good one at about 0.25 degrees. And that's a good observation. It must have been updated by now. So you start with 25-kilometer observations and 25-kilometer model to be able to compare apples and apples and not to go very high. But if you have stations which are not in that, and then you can slightly go higher and check whether what works for you is best. You can make your decision by doing some experiments like that.
So take home is data and stations help to improve, and at least you've got better things to compare to. So.
Yeah.
Okay, one last question for Nerali, very quick one if you could answer this quickly. The sea surface temperature data you can pull out of these records. There's a question of linking that Indian Ocean dipole to sort of cyclone events. Is that something that's it's in the future, or is it something that people are doing now?
I don't know if that's in the future. I know that there has been work from using cave records in northwest Australia to link that to cyclones through the flood events that we can see as we get layers of sediment that become trapped within those speleothems cave deposits as they're being deposited. But we also know that there is a link between the El Nino Southern Oscillation and the Indian Ocean dipole. That's something that this 500 years of data has shown us quite clearly, that when the variability of the El Nino becomes reduced, then the variability in the Indian Ocean also becomes reduced. And we know that both of those factors and the way that they alter the temperature of the ocean have an effect on the number and the intensity of cyclones. And so I think that that's a very rich area for future research, and particularly when we kind of look at what we're seeing this year with the number of cyclones and hurricane events that are happening as the oceans are warming.
Good point. Okay, now we really are running out of time. I'm going to ask everybody to have a 1-minute summary statement. So let's go with Sri first. Could you do a 1-minute summary of your sort of looks on things today? 1-minute summary.
So we look at the global models and then do the downscaling for impacts, and you look for extremes, which is always a challenge for the models to capture. And once we have some idea, then it's used for impact studies.
Cool. Nerali, would you like to summarize the importance of paleo data? I like it, but others, here's your chance to sell it.
Yeah, I think the value of paleoclimate is that it brings another line of evidence. And we know that across all of our data sets, no data set is perfect, no model is perfect, but they are useful. And when we can bring these different lines of evidence together and see what are the common stories that they're telling us, then we can start to have make some really strong conclusions about how the climate is changing and what we can expect for the future. So I think that building those bridges and learning to talk the language of other fields and disciplines so that we can make those connections is a future direction that'll bring great results. Great,
thank you very much. And Odan, you got a minute to summarize if you could.
Yes, well, just to go back quickly to knowledge and theories and tool that was in the question, I think we really miss more constraint on the landslides themselves and on the rainfall extreme. And so there is really a need to combine different methods like remote sensing, satellite observation of rainfall, climate model at high resolution, to couple that, and maybe to try to include that into theories of landscape coevolution. So not forget that landscape have an history, and they are not just responding to the event as an instantaneous impact, but really they depend also on what has happened maybe on the last century or millennium. And that's where also the paleoclimate data can be very important if they have the resolution to see what happens in the relatively recent past.
Great. Okay, maybe if Kristen, could you just say just maybe a minute of summary from your end, and then I'll say something, and then maybe we hand it over to David to get ready for the next session.
All right, thanks, Adam, and thanks all the panelists. Yeah, I mean, it sounds like what I'm hearing is kind of what Odin was saying, that we need to be able to combine all of these different tools, and I think this panel is a nice example of this, where we do combine the landscape understanding, the geomorphology, the paleo understanding with these paleo records, and then the modeling and refining the modeling moving forward. And to me, what's important is that all of these people from these different areas communicate with each other. And so the geomorphologists maybe tell the modelers what data that they really need to be able to predict these hazards moving forward. The paleo people feed their paleo data into everyone else. And I think with this combination, we can start to make some more progress.
Great, thank you, Kristen. I think what I just want to say is I'd personally like to thank Sri, Nerali, and Odin and David for participating. I think we deliberately set out to try and pull some very broad perspectives. I think we've been pretty successful at that in this very short 45-minute window. We've got a couple of minutes left. I think the key thing, my take home for me here, is that the interdisciplinarity of this type of work is fundamental. That paleo has to be used to inform our model development. Our model development has to be driven by the needs of people like geomorphologists that are trying to model the evolution of landscapes into the future. And I think integrating all this together is such a fundamental thing. I think this session that we propose here is going to be a great session when we get to 2021, and we hopefully do get to Yogyakarta, and we can all sit in the shadow of a volcano and talk about how we can integrate all these records. And so with that, a big thank you to everybody for the Q&A. We can't possibly get through all of those questions. You as attendees can't see them. I can see how many there are. And keep chatting amongst yourselves through the session. We'll try and get some of the panelists to answer some of your questions. And then with a couple of minutes to go, I'm going to hand over to David, because I think David's introducing the next session as well. So we'll have what we hope will be a pretty seamless transition. And session one attendees, you may step down, go and get a coffee, relax, and thank you very much for everybody for being involved. Great to see more than 300 people here.
Okay, thank you very much, Adam.